Welcome to Moth Magic, an introduction to moths, being brought to you by Roger Kendrick from Hong Kong. This is the third of 5 episodes looking at moths. So we've looked already at what is a moth, looking at diversity. This episode we'll be looking at survival strategies, and later on we start looking at ecology and how to record moths. Survival. We'll look in this episode briefly at some of the drivers of survival, and principally at the concept of a food web and processes of life cycle within that web that gives rise to various mechanisms in both adult larval form of moth for survival. So here we go. Most people think of the web of life actually as the trophic interaction, the sort of bottom to top approach of production and consumption, which is a process within the web of life of how species interact. Now, moths are not primary producers, they are primary consumers, at least in the larval phase. What about the adults? What do they consume? Well, apart from nectar and pollen, not a great deal. So they're not really consumers in the context of this particular process. They are, however, major items that are consumed by secondary and tertiary consumers. So the web of life takes into account not just production and consumption, which is a process, but other processes like pollination and recycling. And the web itself, of course, comprises all the species, not just butterflies and moths, that make up life on Earth. So a bit more interaction, as an example, would be from the caterpillar through its output, through bacterial interaction from the output, forming extra nutrients for the forest to take up and grow. And this plant growth then becomes food for the caterpillar. You form a cycle. But of course, plants don't just get eaten by caterpillars. They get eaten by all sorts of things. And some leaves don't get eaten at all. They end up on the forest floor as part of the leaf litter. Caterpillars come in and eat that too. There's a whole guild of species, some of which are larvae of Lepidoptera, that recycle, and without which the leaf litter would simply pile up and pile up and pile up. Now, that's just an example. One of the points that might be worth mentioning here in the whole process is the concept of how things adapt to climate, habitat, and over time. So in the tropics, for example, these processes happen very quickly, many cycles in one year, whereas in temperate climates, where you may have very distinct seasonality, probably 1 or 2 cycles per year. You go further north, or perhaps further south, then things happen even slower. You may not have forests, it might just be very, very short, low growth tundra, for example. And that doesn't provide enough sustenance, enough food for the caterpillars to go through their cycle in 1 year or less. It may take many years. And all of these different components that form drivers of evolution give rise to many different pattern elements for adult and larval forms of the moths. So basic crypsis, where a moth looks like its background. It hides away by day, resting on a tree trunk, resting on a stone, looking like a dead leaf, looking like a half-eaten leaf, or perhaps like a broken twig, or perhaps butt end of a twig. Many different forms of hiding, of crypsis, looking like your background. Looking like other things can be taken to a slightly different level, looking like bird droppings, animal droppings. Now, is that Batesian mimicry? Well, that's a moot point. Batesian mimicry is a non-poisonous animal looking like a poisonous model, whether that's a species or some other distasteful component like a bird dropping. Moot point. The point is that really it's a non-poisonous moth looking like something that's either poisonous or distasteful. So it could be a bird dropping, or perhaps you're mimicking something bigger. In this case, trying to look like the face of an animal. So the big eye spots make the predator believe that the prey item is too big for it to deal with. Now, if the predator doesn't buy that, and it didn't here evidently, then bye-bye to the wing. Some bird has tried to poke or even peck the wing towards the eye spot of this big atlas moth. Now, atlas moth actually has two deflection points here, not just the eyes, but also the apex of the forewing looking like a snake. So the eye of the snake, the mouth, and the whole shape of the apex like the head of the snake. Mimicry, though, is taken to a completely different scale and a different league in terms of how clever the mimicry is by things like the clearwing moth. This is over 1,000 species, and each species looks like a different poisonous wasp or maybe a bee species. The mimicry in some of the species is so effective that even the moth, the waist of the moth at the first and second abdominal segment, is narrowed to mimic the narrowing of the abdomen in wasp species. Another group that does excellent job of mimicry, not just visually, but also behaviorally, is the Coryutidae or leaf skeletonizers. They have eye spots at the top end of the wing, or bottom end of the wing, depending upon where one's looking from, that mimic the eyes of jumping spiders. And the way the moth rests like a little wedge and jumps around on the leaf looks just like a jumping spider. So that's another superb example of Batesian mimicry, something non-poisonous mimicking something that is poisonous. Let's take this a little bit further. What if the moth itself is poisonous? These three species here are all burnet moths, and they're all poisonous. Now, I don't have examples of what they look like in other components of the animal world, but the one on the left and the one on the right both mimic other butterfly species. The one in the middle mimics bug species, all of which are poisonous. So where you have a group of species that share the same pattern elements, they're all poisonous, we term this Müllerian mimicry, a mimicry ring, where everything in the ring is poisonous. Now, one approach is looking like something else. Other approaches provide combinations of some of the previous concepts. Here we're combining camouflage, the crypsis, so the forewings are all camouflaged, with fright coloration, such that the hindwings use aposematic colors, bright and simple patterns that are easy to recognize and startle. The moth lifts up its forewing quickly, reveals the bright colored hindwing, gives whatever the predator is a bit of a scare, perhaps, at least time enough to think about what's going on, and in that time the moth makes its escape. Acherontia, this is the death's head hawk moth. There are three species, actually, one in Africa, two in Asia. They take the same approach. They have superb camouflage forewing. They have a classic aposematic hindwing, so that if the predator busts through the camouflage, the moth has time to frighten the predator. And it actually has one other trick up its sleeve to help scare the predator too. It has a short, stout tongue for raiding beehives. I'll come to that in a minute. But it can also squeak because the stout and short tongue resonates when air is forced through it, which is kind of a surprise element. If we pick up one of these guys gently, they may well squeak and we go, whoa, what on earth? So it uses crypsis, it uses fright coloration, and it uses an audio warning to deter predators. Now, that short, stout tongue is used inside a beehive to raid the honey cells, because all Acherontia eats as an adult is honey. And to get in to the beehive, it uses that audio squeak plus the visual. The death's head mask, when we turn it around, actually is supposed to mimic a bee, and it's good enough that worker bees are fooled. And there's one other trick up its sleeve which I can't show you because we don't have smelly vision. If we were able to have this in the field as a visual in your hand, you put it up to your face and you smell, and it's supposed to smell like a bee. So smelling like a bee, sounding like a bee, and looking like a bee all help this moth get in to raid the beehive for the honey. Back to the sound. Tiger moths and bats have long since thought, over 40-50 years, to be in an evolutionary arms race. Bats use echolocation, very high frequency sound, to locate prey items, and tiger moths are main prey items for bats. Problem is, and this was pointed out by Kawahara et al., who acknowledged that there's an amazing diversity of ultrasonic hearing organs in nocturnal moths. It was put by them that actually we haven't really done enough work to find out what the driver is. They identified 9 different evolutionary origins of hearing in moths, and that's represented in some way by the diversity of hearing structures exhibited by different moth families, because no two moth family has exactly the same hearing mechanism. And for the main families that we're interested in for this particular example, the Geometroidea, the Noctuoidea, the Paraloidea, and the Drepanoidea, that's the hook tips, the loopers, the owlet moths, and the grass moths, all evolved something like 90 to 75 million years ago, which is millions of years before echolocating bats evolved. Therefore, these sound detecting mechanisms cannot have been driven, evolutionary speaking, by bat evolution. So what is it then that has caused sound in these families to be detected? Don't know. So, as an example, here is an ear for a moth. It's on, in this particular noctuoid species, the 3rd thoracic segment at the side. In the paraloids and in the geometroids and in the drepanoids, it's actually on the abdomen in various different places close to where this is, but not the same spot. Now that's enough on the adult stuff. On the larval side, well, many of the same approaches are utilized. So crypsis, and I'll explain a bit more about the crypsis of Acherontia, this yellow caterpillar, in a moment, and Batesian mimicry in terms of the hawk moth caterpillar looking like a snake, or this tussock moth caterpillar looking like a bird dropping, or this lobster moth looking like a little ant. Yellow? Why is that cryptic? Well, think of what the sun does. If it shines through the canopy, green leaves actually look much paler, more yellow, when looked at from below when the sun is strong. What other ways do moth larvae try and survive? Well, by hiding. Now, adult moths hide by resting flat on a surface, but the larvae take this to a slightly different extreme. They can build their own shelters. They can create their own shelters, or they eat into a leaf to form their own shelter inside the leaf. Back to warning colours. This is another burnet moth. Hydrogen cyanide being advertised as do not touch, do not taste. Bristles, hairs, also loaded with poisons, loaded with toxins. These are not things that you want to be stroking. They are not cool cats to stroke. But effective? Well, maybe. More on that in part 4. So, summing up then, survival strategies. These strategies are all driven through the diverse array of predators that the moths face. Mostly they rely on mimicry, through mimicking the background, crypsis, or mimicking something distasteful when you're not poisonous, Batesian mimicry, or forming part of a Müllerian mimicry ring where everybody in that ring is poisonous. And the use of colour, pattern, bristles, and poison all help these moths survive. Other approaches, the concealment, using sound, using scent, and using time. The word phenology means how or when over seasons or through the year something is seen or recorded or documented, and time is a strategy to evolve good survival techniques dependent upon climate. Now, we'll be looking at some of these issues a bit more detail in part 4, where we're looking primarily about how the magic of moths benefits the rest of life. Okay, that's all for now. Thank you very much for joining us. Back for part 4 soon.